Hi guys, hope all of you are doing great. I'd like to welcome each and everyone on board. I'd also like to give a special thanks to new members who have joined the group. I'd like to request us to encourage more. Kindly go to YouTube and search Honesty Sciences and Mathematics TV channel and subscribe and engage us on the comment section so that we can be having a healthy discussion and bring more of our members on board so that we assist one another in these various areas of mathematics, physics, chemistry, and biology. So in this case, today we're going to look at one of the ways of describing the electromagnetic radiation energy. And having looked in our first video, the concept of electromagnetic radiation, which we basically defined as energy that is carried through space by means of wave-like oscillations. Therefore, this implied the concept of a wave. So today we're going to look at various ways in which we can be able to describe this aspect of energy. And through experimental data or investigation, or rather through some experiments that were done, of course, we're going to see that there are various ways in which we can be able to represent this electromagnetic radiation energy. Now, I can have just a small recap on some of the experiments that were done. We are going to see that these experiments were launched by Max Planck. Of course, there are various other scientists that we're going to see who contributed heavily towards this particular description. But Max Planck did various experiments, and they suggested that these electromagnetic radiations are emitted in form of tiny packets, which he later called a quanta. So in this case, this packet of energy, we refer to it as a quanta, which we basically going to see being advanced into the topic of broader topic of quantum mechanics. So in this case, this quanta or this packet of energy that was described by Max Planck was referred to as a photon. So in any case, if we mention the concept of a photon in any of our discussion, this is going basically to refer to this concept of a packet of energy that was described by Max Planck during this specific period, which was the 19th, between the middle and the late 19th century. So in this case, Max Planck's idea was advanced by Albert Einstein. Einstein was a famous scientist who came up with, of course, the theory of relativity that we're going to see in some of our topics. But Albert Einstein further confirmed the energy of a photon of electromagnetic radiation, and he said that this energy is proportional to the frequency of the radiation, and of course not the intensity. So he tried to look at these various aspects of this energy of electromagnetic radiation and the intensity and the frequency, and he later concluded that basically this energy is, of course, as a relationship with, of course, the frequency and not the intensity of this particular kind of radiation. So we're going to see the relationship that exists between the Max Planck and Albert Einstein's relationship of, or rather the description of this specific energy as per Max Planck and Albert Einstein in form of equation. So we had written a formula in our introductory part of this specific video on electromagnetic radiation, and we said that we can be able to describe a frequency that was given as mu as the ratio between the speed of light and the wavelength, which is c lambda. Now in this case, we're going to see that from Max Planck's argument, this is a Max Planck's argument, it described the energy of these particular particles using the formula of H frequency, and it was trying to give the relationship between the energy and the frequency, whereby this H implies the Planck's constant, which is of course a figure that is known, and this other one refers to frequency, whereas this one is the energy of this specific radiation. So therefore, having looked at this specific aspect of frequency as the ratio between the speed of light and lambda, therefore we can be able to expand this aspect of this formula for energy and say energy can be given as Planck's constant, and then give that one as such. So this is going to give us our first part of our equation. Of course, we are going to have other subsequent ones, but I'd like us to note how this specific equation is given. Sorry for that. So therefore, in us describing the energy of a photon, then therefore we can give it from this general formula as this specific product for Planck's constant and the speed of light over lambda. And this is energy is going to be given in form of kilojoules or joules as it may be required. Now there are some other cases which we're going to encounter whereby this description of this specific energy is going to be requested, or rather we're going to be requested to give it in kilojoules per second. Sorry for that, kilojoules per mole. And we have described the concept of the mole, of course, as specific from Avogadro's constant and the number of, we said that this particular case of a packet of energy, which is a photon, can be referred to as a particle. And in this case, from the concept of a mole, we said that there are specific number of particles which make up of a mole. So therefore, if we treat a photon as a particle of energy, therefore we're going to have it given as Avogadro's number of particles which is of course also another constant which is given implying this particular mole that we are talking about. So in any case, if we are required to give energy in form of kilojoules, then we can be able to give it an illustration. But in any case, if we are asked to give it in kilojoules per mole, then we will require this particular conversion from Avogadro's number in order to find energy of kilojoules per mole. So I suppose we just perform or do an example to illustrate this is first part of our equation, or just giving an example to just create an emphasis for this part of our equation. So I'm going to read our question so that we can be able just to do an example from that. And this question goes like this. So this is information from our sample question 1. Calculate the energy in kilojoules of a photon of red light with a wavelength of 656 nanometers. So we have been given the wavelength of 656 nanometers, and this basically is the wavelength of a red light, whereby we have been asked to calculate the energy in kilojoules. So we have said energy of a photon can be given as hc over lambda, and we said that h is the Planck's constant, which is of course a known constant, 34, and this is joule seconds. And the next that we have been given is the speed of light. So I'm just going to reduce this one so that maybe we can 6.63 10 negative 34, and then with the product of 3.0 times 10 8. This is in meters per second, joule second, and then we are going to have this one over 656 times 10 negative 9 meters. So whenever this one is in nanometers, we're going to convert this. This one is in standard units, joule second, this is meters per second, and then this one is given in form of meters. So I'm just going to have this one given in their specific units so that we can be able to see how the units of course are treated. So in this case, this is joule seconds, and this is meters per second, and this is in meters. So therefore, if you try to look at this aspect of the units, or rather try to figure out which units are we going to give this particular energy, therefore we're going to see that the meters and seconds are going to leave us with the joules. But we have been requested to define that specific amount in kilojoules. So therefore, it's going to be a division over 1,000. So there, whichever amount of figure that we're going to find at that specific point is going to be a division of 10 negative 3. Therefore, this is going to give us, can just do an evaluation to confirm that one. And if you find a different figure, kindly inform us on the comment section so that we can be able to do a rectification for that. So this is going to be kilojoules, which is going to be the energy of this particular photon of red light with a wavelength of 656 nanometers. So basically, from our first video on the description of various aspects like the wavelength and of course the frequency, we can see that we have advanced to this particular point whereby we're going to calculate the electromagnetic radiation of these various energies, of course, which we have said are referring to the transitions that we're going to encounter. So in this case, we're going to look at our next topic on the specific model that we had looked at on the different models of an atom. And basically, we're going to look at Bohr's model and try to see that some of the various, of course, shortcomings and the advantages that we can be able to borrow from that in trying to, of course, achieve our objective of describing this transition energy. So for today, we'll stop there. Kindly catch us in our next video as we're going to look at another topic still on this specific part, which is going to assist us in trying to specifically describe the various transitions that we have been mentioning in some of our videos. So that is it for now, guys. Bye. God bless you.